So in video 4 on discrete probability, we're going to look at the idea of independent events. And the basic question here is our key question, is whether an event E depends on or is it independent of the occurrence of some other event F. So to get at this idea, let's revisit an example that we've already looked at where we take and roll two dice and take the sum of the die and record the results, which in this table are recorded in red. And in a previous video we looked at the probability that the sum was a 5. We looked at the probability that the sum was a 7. And we looked at the probability that the sum turned out to be a 9. And to calculate these probabilities, it was just a straightforward matter of counting the number of 5s. So for example, 1, 2, 3, 4, and then dividing it by the number of sums that occur in the table. And there are 6 times 6 is 36 possible sums. And for the 7, we get 1, 2, 3, 4, 5, 6 ways that we can get a 7 out of 36 possible sums. And for 9, we get 1, 2, 3, 4 ways that we can get a 9 out of the 36 sums. And then we looked at what was the probability that we got a sum of 5 given we rolled a 6 on the first die. And then we looked at the probability that we got a sum of 7 given that we rolled a 7 on the first die. And we looked at the probability that we got a sum of 9 given we rolled a 9 on the a 6 on the first die. These should both be 6s. Given probability of 7 given we roll a 6, probability of 9 given that we roll a 6 with the first die. And to get these probabilities, we realized because we had already rolled a 6, everything that could happen is happening in this row in the summation table. And so we have a reduced sample space, and we say, well, what's the probability that we get a 5? And we look through the possibilities given that we've rolled a 6, and we saw that there was no way to get a 5. So 0 of the 6 possibilities were a 5. We saw that 1 of the 6 possibilities was to get a 7, and we saw that 1 of the 6 possibilities was that we would get a 9 for our sum. And then we noticed that the probability of 7, which was 6 over 36, reduces to a 6th. And we saw that the probability that we got a 7 was 1/6, whether or not we had rolled a 6. And when we scaled this up by multiplying by 6 over 6, we got 6 over 36. And so what we had seen was that the probability that we got a 5, given a 6 had been rolled, changed the probability over the original probability. It decreased it to 0. The probability of getting the sum of a 9 was improved to 6 and 36 from 4 and 36. But the probability that we got a 7 was completely not impacted by whether we had rolled a 6 on the first die or not. So what we would say is that the probability of getting a 5 and a 9 were both dependent on what happened on that roll of the first die, namely the rolling of the 6. Our probabilities were dependent on that roll. The roll of the 6 changed the probabilities, whereas 7 was independent. It didn't matter what happened. When we rolled a 6, the probabilities remained unchanged. And what we want to do is kind of concretize this idea from a formulaic perspective. So here's the idea. The idea is that if you have an event E, if E is independent of whether event F has occurred or not, so event E, the event that we get a sum of 7 on the roll of 2 dice, event E that we get a sum of 7 on the roll of 2 dice. If event E is independent of event F, say we roll a 6, then the probability of E should be the same regardless whether event F has happened. In other words, the probability of E should be the same as the probability of E given F if F has no impact on whether E is going to occur or not. So from there, once we can just kind of internally justify or conceptualize the idea that if E doesn't depend on F, then the probability of E should equal the probability of E given F, we can say, well, from our previous video, we established that the probability of E given F was just the probability of the intersection of E and F divided by the probability of F. That was from our conditional probability video. So that means that demonstrating that the probability of E is equal to the probability of E given F is the same as demonstrating that the probability of E is equal to, if we have independent events, the probability of E intersect F divided by the probability of F. If these two are the same, and this is the same as this, then by transitivity, we can replace this with this. And once we do that, we just multiply both sides by the probability of F, multiply both sides by the probability of F. The probability of F's cancel, as long as the probability of F isn't 0. And here we wind up with what is the classic test for independence. This is the classic test for independence. So if the probability of E does not depend on the probability of F, then these two probabilities should be equal, which means that the product of the probability of E and the probability of F should equal the probability of the intersection. So this is our classic test for independence. So let's apply it one time. We'll just have one example. So let's read through the example. Suppose E is the event that a randomly generated bit string of length 4, so a sequence of 4 zeros and ones, begins with a 1, and F is the event that a randomly generated bit string contains an even number of ones. Are E and F independent if the 16 possible bit strings of length 4 are equally likely? So in this case, our sample space, S, is just bit strings of length 4. 1, 2, 3, 4. And we know that we have two possibilities for each bit, which means we have 2 times 2 times 2 times 2 possible bit strings of length 4. So we know that the size of S is equal to 2 to the 4th power, or 16. And we've seen this in a previous video. So now we have two other events. The event E, it's sample space, and now we have two events. And the event E is the event that a randomly generated bit string of length 4 begins with the 1. So for event E, we want to begin with a 1. This is begins with, ooh, that's horrible. Begins with a 1. So that means there's a 1 in this slot. And if you put a 1 here, that means you don't have any choices, but you do have 2 choices here, times 2 choices here, times 2 choices here, and only 1 choice here because you're starting with the 1. So the size of E, the event that you begin with a 1 for your 4-bit string, the size of that is just going to be 2 cubed, or 8. F, on the other hand, what does F look like? F is the event that a randomly generated bit string contains an even number of ones. So even number of ones. So if we have a bit string of length 4 and we need an even number of ones, then we either need 2 ones or we need all 4 to be ones. Either 2 ones or 4 ones to have an even number of ones. So we look at this and we can think about combinations, I believe, in this case. We can say, look, I have 4 places into which to distribute zeros and ones, and to have an even number of ones, I either need to choose 2 of those slots, or so that's going to be a plus, or I need to choose all 4 of those slots to get an even number of 1s. And here 4 choose 2 is going to be, what is that, 6? 4 choose 2 is 6 because we get 4 factorial over 2 factorial. 4 minus 2 is going to give another 2 factorial. So we'll get 4 times 3 divided by 2. Yeah, that's 6 plus 4 choose 1 is just 1. So 7. So the size of f is equal to 7. There's going to be 7 bit strings of length 4 that have an even number of 1s. And we have what? So we need to know the probability of E, we need to know the probability of F, but we also need to know something about E intersect F. So let's talk about E intersect F. E intersect F needs 2 conditions. It needs to, E says it needs to begin with a 1 and F, even number of 1s, and have even number of 1s. So let's think about a bit string of length 4 that meets both conditions. It has to begin with a 1 and have an even number of 1s. So if there's a 1 already in this position, there's only going to be 2 ways to get an even number of 1s. One, we can take the 3 remaining spots, 3, and we can choose one of them, which will give us 2 1s. Or there's a plussy, or we take the remaining slots, 3, and we choose all 3 of them. And then that's just going to equal, this will simplify to 3 because it'll be 3 divided by 1 factorial times 2 factorial. The 2 factorial will cancel the 2 out of the 3 factorial and leave us with a 3. And 3 choose 3, there's only one way to do that, so there's going to be 4 elements in that intersection. So the size of the intersection is going to be 4. And now we just look at the 2 pieces. What's the probability of the intersection? E intersect F. Well, the probability of the intersection is 4, the size of the intersection, divided by 16, the size of the sample space, or a quarter when we reduce it. And then we need to calculate the probability of E times the probability of F. And the probability of E is just going to be 8, the size of E, divided by the size of the sample space, which is 16, times the probability of F. F has 7 elements in it, not plus, times. Has 7 elements in it, over 16 is the size of the sample space, so this is really a half times 7/16, or 7/32. And what we notice is that the probability of E times the probability of F does not equal the probability of E intersect F, which means that E and F are dependent events. E depends on F. We have dependent events. E depends on F.